And the topic here is Campana's program, and I started introducing it in terms of something which is not Campana's program, something, but it serves as a motivation that we need to do something new to varieties, to add some structure to varieties. And the problem we are trying to resolve is to understand between varieties of general type, which Lang conjectures have few rational points, and varieties of Kodaira dimension 0, which Campana conjectures have many rational points, and there's some evidence for either one of them. And we need to understand what happens in the middle. And that's the topic of Campana's program. It actually suggests a resolution. The resolution is in the nature of what Darmon asked last time. We noticed that it is not the case that we can tell whether a variety has many rational points or not just by checking if it has a dominant map to a variety of general type. But what Campana says is instead of a variety of general type, we should look for other dragons of general type or something of the nature. And once we do that, we should have the complete answer. Okay? Now, there are not dragons. There's something else. So the first example that we had was this surface S2. And I put this just to remind you of this warning here. The surface S2, which was obtained as a quotient by a Zemo 2 action of something, and the surface S2 looks something like this. It's an elliptic surface over P1, and it had a certain number of double fibers. So to make them double, I'll draw the fiber double. So this is just suggestive. So there are 2G plus 2 points in P1 where the fibers are double. And we went back to the work of Darmon and Granville, which tell us that what we need to consider is the fact that this map from S2 to P1 factors through this orbifold P. The orbifold P, which is what I called the square root on P1 of D. So let me just tell you a little bit about, people ask, how do you define orbifolds, or to be precise, algebraic stacks? And let me just tell you bluntly, I'm not going to define algebraic stacks in 3 hours, okay? Which is what I have left. The complete definition, that's ridiculous. This is like asking, can you give the foundation of the theory of schemes in 3 hours? Okay? So I hope Andrew agrees. Where is Andrew? Okay. So, all right. So, but what I can tell you a little bit is, so let me move this a little bit. I can tell you a little bit about what are maps. What are maps from a scheme S, maybe I shouldn't call it S, a scheme T to this orbifold P. So a map from T to an orbifold P, as the notation suggests, so I called it. So a map is just a map to P1. So this is F and this is F bar. So I have a map to P1 such that up to a unit, the defining equation of D becomes a square. So to be precise, a map F is given by the following data. Is a map F bar from T to P1, a line bundle L on T, and a section t in h naught of TL. So it's a gadget of data such that, sorry, and I forgot one more piece of data, and phi, where phi is an isomorphism from L squared with f bar upper star of O1, sorry, f upper star of OP1 of D. So you pull back the divisor, then L is a square root line bundle, and T is a square root of the defining equation. And so phi of T squared is the defining equation. Is a f upper star, sorry. Okay? So basically up to units, the defining equation becomes a square. And if you think about it, let's just look at the generic case where T does not map into the divisor D. These 2G plus 2 points. Then in this case, all that it means, if D is irreducible and does not map into D, all that it means is that D becomes a double divisor. So f bar upper star D is twice some other divisor, which I don't know what to call it, E. Okay? So, a point of this crazy orbifold is a point of P1 where the divisor, a schematic point of P1 where the divisor becomes double, essentially. And we'll get back to that when we talk about integral points on such things. Well, maybe I should say, so in particular, if I consider P and I spread it out over spec Z, let's say, so I spread it out like this. So when should I consider a rational point on P1 to be integral? So if I have a rational point on P1, it corresponds to a section. Where was my red pen? So a rational point corresponds to a section. And what this says is that when I pull back the divisor D, well, what do I get? So a rational point is a section. So this means it's it's a map of a spec Z to P1. I pull back the divisor. What do I get? I get a divisor on spec Z. Namely, I get a fractional ideal. But this is actually an effective. So it's truly an ideal. And what I'm saying is that this ideal is so if I have a point, so I'll have, so this F is going to be a section, then F upper star of D should be well, it's a fractional ideal. It's an ideal, and it's so all the multiplicities have to be even. So that's kind of an explicit way to say it. So I just wanted to say what these things are. Okay, so let's go back here. So Darmon and Granville said that using Chevalier-Wade, this is, once you have this description, you can just go and do it. It says that an orbifold curve has potentially dense set of integral points if and only if the Kodaira dimension is less than 1. And one crucial point is that since S2 maps to P, then integral point on S2 map to integral points on P. But S2 is proper, so integral points on S2 are rational points on S2. So if P is a rational point, so this is the same as S2 of OKS. There's nothing here. But if I extend S2 over the OKS in such a way that the map still exists, and of course after inverting some S, after enlarging S, I can always do it, then the image is going to be an integral point. I have only finitely many points here, therefore so this completely explains from this theorem, completely explains why S2 does not have a dense collection of points, because an integral point on P since integral points are not zeroistically dense, and since rational points map to integral points, the rational points here are not Zariski dense. So this is the true orbifold picture which Delmont and Granville developed for the case of curves. Say again? I'll tell you exactly when I want to consider this. Okay. Well, you can, but when yeah, I'll tell you what I want to consider in a minute. So I think I need to remove this and this. So here comes Campana. And Campana notices that at least in higher dimension, but also some examples of surfaces are of interest, that there are other cases that, of vibrations where you want to attach a number. And the question is, what should we declare the structure to be given when the fiber looks like x squared times y cubed instead of just x squared? So when we had, I removed the picture, we had double fiber, the function down on P1 was x squared. That's what made it to be a double fiber. But what happens instead if you have, now I need another of these, if you have like this, what happens, so the original picture was like this. We had t equals x squared. So this is x and this is y. Y is inconsequential for this picture, but t equals x squared. Now another picture is when you have, so this is the double fiber. Now if you have one double fiber, one triple fiber, so this is, well, x and y. So this is t. Maybe the way I drew it is t equals x cubed y squared, or did I do the other way? It doesn't matter. So what number should I attach to the fibration in this case? If you go back to the orbifold, the classical, here's Andrew. You kept quiet. If you go back to the classical picture of orbifolds, Andrew will tell you the correct multiplicity to put is the GCD of 2 and 3, which is 1. Because if you, you can certainly lift a map. You can locally lift a map which is double at t by lifting it over here. You can lift a map which is triple by lifting it here, and you can easily show that. Then you can also lift. There's a lifting that is a quintuple and so on. So in order to put an orbifold structure, so the degrees of maps that can occur, the divisibility of them is, there's no condition. So the GCD of 2 and 3 is 1. But Campana says, and that luckily Bogomolov is not here, so I'm not going to go into so the fundamental reason behind it is a subtle geometric structure. So Campana says that for differential geometric, from the differential geometric point of view, and that goes back to Bogomolov sheaves, which I will not discuss, a very interesting theory that comes about is it occurs if you attach to it not a number 1 but a number 2. What this does for you, well, first of all, it means that you're not really using orbifolds. And a second thing, it says that you cannot use Chevalier-Weil to reduce things to Falting's theorem, but it does give you a very, very interesting theory with a lot of interesting conjectures already for curves. So here's a definition of Campana. Suppose I have two smooth varieties and a dominant map. And remember, I had this thing that this is under construction. I'm not sure what the condition. Let's say that it's a proper map, but I'm not sure what exactly I need. And I'm assuming for now that the dimension of y is 1, because then the theory is sort of well developed and well understood. And then I will struggle later on today and tomorrow to understand what happens in the higher dimension. That's really, really subtle. But dimension 1, I understand sort of what's happening. You define a divisor with rational coefficients, just as before with the Damont-Granville example with the S2. We took the divisor of points and we put it with multiplicity 1/2. Now you define a divisor with rational coefficients. The coefficients are called delta p. So this is a Q divisor on y. So these delta p's are rational numbers. Maybe I should point this way. These delta p's are going to be rational numbers. And the way you calculate the delta p's is you look at the point P, that's a divisor, you pull it back, that's a divisor upstairs, and you look at the multiplicities that it occurs. That's exactly what we were doing, we were asking before. And the multiplicities, maybe I should draw a picture again. Well, it's this picture. So you took the point P, you pull it back, so this occurs, so what you get is, if this is C1 and this C2, then you get F upper star P is 2C1 plus 3C2 in this particular example. So the MI in this example are 2 and 3. So CI are just the components of the fiber taken with a reduced structure, and the MI tells you in which multiplicity they occur in the fiber. And then you set delta P, this multiplicity, to be 1 minus 1 over MP, where MP is the minimum of the MI. So you take the minimum rather than the GCD. That's Campana's crucial departure from the classical orbifold picture. Now I'm a bit confused here. I'm missing a transparency. Go ahead. Yes, so that, you're forcing me to tell you something about Bogomolov sheaves. So what the differential geometer will tell you, you need to think about differential forms. And what you're asking yourself is take a differential forms upstairs with rational coefficients, but pluricanonical differentials, and ask what differential forms downstairs. You look at the map from, so dimension of y is something. So this is F upper star. So you have a map of regular differentials and you can take sim n of this. Oops. Sim n of this. So you take, this map to sim n of wedge dim y omega 1x. That's a natural map. And you ask yourself, what poles can you put here so that it becomes regular? So you take the maximal pole that you can put here so this becomes regular, and as a map of sheaves, and you declare the fractional divisor to be what you get. Okay, so for each irreducible divisor, this gives you a well-defined integer, multiplicity, m. We'll get to that in higher dimension. Okay? So these are what's known as Bogomolov sheaves. These canonical sheaf on y with rational coefficients such that it becomes regular upstairs. This is a Bogomolov sheaf. But I'm deliberately not going into it. What did I want to do? No, I wanted to do this. Okay, so So that gives you a divisor with rational coefficients on y. And what Campana then does is it says, well, let's decide from now on that to codify the notion of a dragon in this way, as a variety together with a divisor with irrational coefficients. Okay, I already have it upstairs. Okay, so a Campana constellation curve. And the one thing I need to correct here, at least the notation should be parentheses on both sides. A Campana constellation curve is by definition a curve y along with a q divisor where each of the coefficients are rational numbers of this form, the kind of coefficients that occur in an orbifold. So so Campana actually called, okay. And the Campana constellation base of a morphism from x to y is the pair y with this divisor, where that divisor is obtained in this way. So whenever you have a map, you have a canonically defined Campana constellation structure on the variety y, on the curve y. So as long as you have a curve downstairs, this defines for you. Okay, so the way it looks, it's very tempting to call this an orbifold, but if this were an orbifold, then this would have to be a morphism into an orbifold, and it's not. That's why I disagree with the use of the word orbifold that Campana introduced in his first papers, because this analogy is broken exactly in the definition of the Campana constellation base. And you'll see that it's broken even more in higher dimension. So that's why I call it constellation. The reason I call it constellation, well, okay, so what Campana said is he agrees that orbifold is problematic, and we try to work on various things and various alternatives, which he disagreed with. And he cannot find a reason to disagree with constellation, especially since he was an astronomy student when he started. And what the picture I see is think of y as kind of the heavens, and you see these divisors, these points with different these are stars with different intensity. And it will become even more compelling when you do higher dimension. I like this picture, and it helped me actually complete these lectures. It's kind of inspiring to think about it this way. But if somebody else finds a better name, then okay. Oh. I can live with that. Yeah, so remember the definition. This you really want to have in your notes. So a Campana constellation is a variety with an orbifold type divisor, and the Campana constellation base of a morphism is given using the minimum rule. So if you think of a map of curves, then you can do it in analogy so when does a curve map to a Campana constellation? So if X is also a curve, then what this says is f upper star of each one of the pi is going to be sum of MQ, where each of the MQ, so the only condition now is that each of the MQ is bigger or equal to the MP, rather than divisible. Okay? You can think about what happens in the number theory. I mean, you have a product of primes with multiplicities. The condition now is not that the multiplicities are divisible by MP, but that whenever the multiplicity is positive, then it's at least MP. So it's a much weaker condition. We'll get to that. Okay, so now let me point out that Campana's definition deliberately does not distinguish between the structure coming from a fiber of type x squared equals 0 and fiber of type x squared times x cubed equals 0. What I will do later with the notion of firmaments supporting a constellation is I will say that, in fact, the firmaments are different. The firmament is not just a number, but a whole semigroup inside the positive integers. But we'll get to that. So in this case, a semigroup is going to be the even integers. And here is a semigroup generated by 2 and 3, which is all the integers except 1. All the positive integers except 1. All right, so we're getting there. Okay. Now we can do some differential geometry before we do arithmetic. The Kodaira dimension of a Campana constellation curve is defined to be the Kodaira dimension, just like we did with an open curve. An open curve you can think of as a closed curve together with a structure of a divisor with the multiplicity 1. Here the multiplicity is less than 1. You do the same thing. So what does that mean? Of course, delta has fractional multiplicities. So sometimes, so if you just take sections of the canonical sheaf plus delta, it's the same as a section of the canonical sheaf. But when you multiply, you take the 3 canonical sheaf, then whenever the multiplicity in delta is less than or equal to 3, you get something new. And therefore, what you get here is exactly what's known as Bogomolov sheaves. This fractional divisor and its multiple give you what's known as Bogomolov sheaves, which I'm not discussing. Okay, so we take the Kodaira dimension of this, which is just the rate of growth of the spaces of sections of these. And an exercise for you to look at is exactly the case of P1 with 2g plus 2. Let's say g equals okay, I was going to say g equals 2, but I drew the case g equals 3. Okay, g equals 3. Well, the canonical sheaf has degree minus 2. I'm putting here delta, which has 8 points, but I'm taking each point with multiplicity 1/2. So what I have is, OP1 of minus 2 twisted by delta over 2. So this has degree 4. This has degree minus 2. You get a positive degree, and you check that indeed you get sections as soon as you take multiples of this of degree at least. So the 2 canonical forms and so on, you start getting sections. So check that the Kodaira dimension is 1 in this case. We say that y is of general type, y delta is of general type if the Kodaira dimension is 1. And we say that it's special if it's not of general type, the Kodaira dimension 0 or minus infinity. And then, what did I want to say? There's an exercise in your notes which says, classify those which are special. You can just say which multiplicity, this is just a combinatorial exercise. Which multiplicities occur in special curves? Those curves are only going to be curves of genus 0 and 1 if they are special. And you can say exactly what can occur. This is a nice exercise in combinatorics, and I actually point you to a place in the literature where it's figured out. So you will never get stuck because it's solved. I'm confused. And the reason I'm confused is Okay? So now I can do arithmetic. You need to speak about integral points on an integral model of the structure. So suppose y is an integral model of your curve. Let's just take this particular example. So I'll draw it like this. So here's a P1 with, and just for simplicity, I'll take the integral model of delta to be just the closure of delta. You could put some stuff in fibral divisors. That's okay, but I'll avoid it for simplicity. And I'll assume that y is proper over some OKS, and delta is the closure. And you define a point to be considered as an S integral. A rational point will be considered as an S integral point on the structure. Sorry. A rational point on y, well, then it's an S integral point on the proper model. You take the closure, it's just, on a proper model is an S integral point just by taking the closure of x. Maybe I should draw the picture again. Here's y, here's the point x. You take the closure, then this is y. I have no problem taking its closure. That's an S integral point. I want to ask, when is it an S integral point on the structure? I should have drawn the point in red. Oops. And here is the divisor delta bar. This, for the time being, I'll only make the statement when x is not in delta. When I say for the time being, in these lectures, I will assume that x is not in delta. So it's said to be a soft S integral point on the integral structure if for any non-zero prime where the reduction of x coincides with the reduction of some element of delta tilde, we have that the multiplicity is at least MP. So what do I mean by that? So I take one of these points here on delta, which I call z. I pull back. So I think of x as a map from fx bar, as a map from spec OKS to this. So x upper star of z, this is going to be a fractional ideal on OKS. So these are primes. These are not the p's. These are Weierstrass p function notation. The ones that number theorists like this curly p, which I cannot draw. I'm sorry. So pi to the mi, and the idea is that mi is bigger or equal to m sub z. So this should be a z here. Z is one of the points in delta, and z bar is one of its closure. So this is all that is saying, which is what is suggested by the definition of a map. Okay, let me remove this. What's that? Yeah, you can throw in the cases of open curves by allowing mz equals infinity. Then it just says that it does not reduce, never reduces to z. And a key property is the analog of the property that we had when we worked with classical orbifolds in the example of S2 mapping to P1. We assume that x to y extends to a good model, script x to script y, so that all the ramifications remain constant. Then the image of a rational point on x, namely an integral point on the model script x, is what I call there a soft S-integral point on. So the reason I call these soft is that so this is a weak restriction. Later when I introduce firmaments, I will have a stronger restriction which I'll call firm S-integral points. Soft S-integral point on y, or y with the model y with the model of the delta. With delta, I'm taking here the delta f. So this is I'm taking the canonical Campana constellation structure on the curve y, and I'm spreading it out. And this is almost immediate from the construction. So for a suitable S, this is that there's a good model, you get such a restriction. In other words, if you want to bound the rational point of x, if you understand this means that it's sufficient to bound integral points on the Campana constellation curve y. Okay? So here's a conjecture of Campana. If y with delta is a Campana constellation curve and is of general type, namely codire dimension 1, then the set of soft S-integral points on any model script y is not Zariski dense. This is exactly in analogy with what Damon and Granville did, but Damon and Granville could prove their case, the true Oberfold case, using Faltings and Chevalier-Vey. This is a conjecture. This is an analog of model which is not known for curves. So there are plenty of number theories here. I think this needs to be proven. There's one little bugging problem in here, that this feels a little bit like ABC. A little bit like ABC because of the minimum thing here. It's much more restrictive than ABC, so there's a chance. But it feels like ABC. It follows from ABC, and that's what's my... So this conjecture does not seem to follow readily from Faltings' theorem. It does follow from the ABC, in particular the function field case. Well, actually, from the function field case, you need to, the reduction, you need to use the proof of ABC rather than ABC itself. But the function field case is a theorem, and which is a very compelling evidence that it should be true. If y is a Campana constellation curve of general type, defined over the function field of a curve, then for any finite set of places in B, the set of non-constant soft S-integral points, this is the analog of model for any. So here's your Campana constellation base, and I spread it out not over spec Z, but over B, a curve B, and I choose some prime set of primes S, finite set of primes to remove, and I'm looking at the model of this. I put my sigma here. This is a sigma tilde. This is y. This is S. And I'm looking for, I need another color. I'm looking for those points which have the appropriate multiplicity restrictions. So they have to be really, really tangent. Well, there's no condition here, but, well, there's no condition here because it's in S, but here I have to have multiplicity and so on. So I'm looking for those points which have sufficient tangency with sigma tilde, as dictated by the structure delta. And it's you know, when this is P1 with 3 marked points, it's easily proven from the usual ABC over function fields. And if you have P1 with more points or an elliptic curve, you need to do something similar to the proof of ABC of a function field, which is actually easy. So read in Campana's paper and yeah. So over number fields, yes. So there's one case of interest for elliptic curves, but then by a simple branch cover trick, you can reduce it to a case of P1. But not, sorry, but is it with 3 points? I'm not, no, it's not with 3 points. You need to work up to 5 points. There's a finite number of cases, but if you have ABC, then you can fold these points over. The problem is that these points have different multiplicities, and you cannot reduce it to Campana because there are different multiplicities, but ABC allows you to do that. Now I have completely messed up the order of things. So we have a conjecture, and the conjecture is, so in particular, what does the conjecture say is it says that to study varieties which map to Campana constellation curves, if we want to bound the rational points upstairs, it's enough to prove Campana's conjecture. Right? The Campana conjecture, which I just removed, which is stupid. This conjecture. If you have a Campana constellation of general type, the set of S integral points on any model is not Zariski dense. Okay? That's a curve case, and now I'm really going into deep waters, where I don't exactly know what I'm saying. Only sort of. Okay, so how did I do this? That belongs there. I'm missing one now. Higher dimensional Campana constellations. Here's the problem with Campana constellations, and that's why I have these extra slides here. Campana constellations are really well suited for curves and for understanding things on curves. If you do just divisors, if you try to mimic this definition for a variety of higher dimension, say you have your map from X to Y, you want to, so here X is something big, and say you want to, it's not hard to attach multiplicities to divisors on Y. We'll do this in a moment. But the problem is this does not specify the structure in codimension 2 where the divisors intersect. So there's a serious problem in defining structure in terms of divisors in codimension 2 or more. And for that, what I'm doing, what I suggest, so Campana just says, I'll have a structure for Y just in terms of divisor. If I choose a different birational model, I have a different structure. And then he needs to take a limit over these structures to say something about the fibration. What I want is, given the fibration, I want to already give a structure on this particular Y, so I don't need to. And in order to do that, I need to understand all modifications of Y. So I need to replace the notion of a divisor by something which takes into account higher codimensional situation. And rank 1 discrete valuations are a good notion, I believe. So What I'm defining now is what I call Campana constellations. Remember that later on I'll have something underlying it, which I call firmaments. So this is the first iteration. There will be a second iteration. A rank 1 discrete valuation on a function field is just a discrete valuation. So what is it? It's a map from the multiplicative group to Z, satisfying the usual inequality of valuations, and with equality if unless they have the same valuation where the sum might have a cancellation. So, and just for completeness, we define the valuation of 0 to be infinity. And the valuation ring is just all those elements of the function field whose valuation is bigger or equal to 0. That's the usual thing we do with discrete valuations. And YV is the spectrum of the discrete valuation. It has a unique closed point, which is called SV. A special case of a rank 1 discrete valuation is one that is obtained from a divisor. In fact, not just from a divisor on Y, but on any birational model on Y. So this one rank discrete valuation is called divisorial if there is a birational model Y prime of Y and an irreducible divisor D prime on Y prime, such that for all X, the valuation is just the multiplicity of X on that divisor. We know what the multiplicity of a function along a divisor is, and sorry, you have a question.
K of 1 and K of 1.
Thank you. There's no X here. And just to specify, we say that this valuation nu has divisorial center D prime on Y prime. For curves, of course, it says it's nothing new. Any birational model of the curve is the curve, if I have a smooth curve. And now I can define a generalization of a divisor with rational coefficients, which is called a B divisor. This is something introduced into birational geometry by Vyacheslav Shokurov in his work on the minimal model program for fourfolds. How did I do that? A B divisor is an expression of the form boldface delta, which is a finite sum. It's a sum, not necessarily finite. Sum CV times C nu times nu, which is possibly an infinite sum over divisorial valuation of the function field. But for each birational model, I want to have only finitely many divisors. So the coefficients have to be rational and satisfy the following finiteness condition. For each birational model Y prime, there are only finitely many valuations with divisorial center on Y prime having C nu different from 0. Okay? That's Shokurov's notion of a B divisor. It's something that looks like a divisor on each birational model. And you can ask all sorts of questions about these. I'll be interested in ones that come out of a fibration. Suppose F is a dominant morphism of varieties. And maybe I need to assume that it's proper. Again, this is we are in rough waters here. I'm not sure what's the precise assumption needed, but proper is probably enough. Dominant morphism of smooth varieties, and probably I do not need smooth varieties, and it might be interested not to assume that, but for each divisorial valuation nu on ky, consider the pullback So I have x going to y. And so I have a divisorial evaluation, so I have some kind of a germ of a variety. And I pull back x. And what happens when I pull back x? I get a germ of a variety together with something ugly, which might be just supported over the closed point, but I throw away the closed. So x prime is a desingularization of the main component, only the good part. So I take this and desingularize it. So this is x prime sub v, it should be. X prime sub v is a desingularization of the main component of the pullback. So you can actually write down a diagram. You have x to y, you have a yv, and you have x crossover yv. And then you make a desingularization of, so this is the new, any desingularization. Yeah, I will only look at the divisorial valuations upstairs. The problem with valuations is that there are crazy valuations. Already in C2, if you take, this is a classic example. You have a rank 1 discrete valuation defined in terms of, so take the graph of the sine function and restrict a polynomial to the graph and see what its multiplicity is at 0. Now that's a discrete valuation, but it's not divisorial. It's in essential way analytic. Okay, so there are many divisorial evaluations. Many discrete valuations. I only want to look at this divisorial ones.
But my question is this: so if you have a field sitting inside another field,
yeah.
K of y sitting inside K of
yeah.
y, and you take a divisorial valuation on K of y,
yeah.
you are looking at all the valuations on K of x that extend that, right? You can always extend them. Are those valuations upstairs divisorial all the time if they sit over a divisorial valuation?
No, because you can put this. So so you map the plane to the. You just map. Yeah, you just map the plane to the curve by. So you just can't escape these really crazy things. They are there, but what you can do is ignore them.
But it doesn't matter, right? Because it doesn't change the minimum?
I think that's true. I think it would not change the minimum. I think that's the reason why I'm happy to use just the divisorial valuations. I'm still in. I'm not a I'm not a valuation theorist, and I feel really queasy about doing this, but I have to do it. So now you can write the pullback of the closed point here. Well, you can think about x prime as a variety over a curve, and the pullback of the divisor, which is the origin, is a bunch of divisors. So the bunch of divisors with certain multiplicities. Then you do the same thing. You take the minimum of the mi, that's called m nu, and you take delta to be the associated orbifold type number. Then the Campana B divisor on y associated to the dominant map is defined to be just in terms of this delta v. So this way I can produce a B divisor for any morphism, which includes all the information of all birational models at the same time, because it's a B divisor. Now, so if you look at Hironaka and Zariski, so the space of all valuations on a function field is the risky Riemann surface of your variety. And things that work on that, people have used celestial terminology to describe them. You think about the valuations as little stars, and each one of the y's as the kind of picture of the heavens that you see with a sufficiently strong telescope. If you get a stronger telescope, then you make a birational transformation. It's like taking a blow up and you see more valuations. Okay, so with the Hubble telescope, you'll see a lot of valuations, but if you're in 100 years, probably they could see more. So the collection of all these valuations is the picture I see is, the heavens with all the stars that you can see for each. Okay. You don't have to keep this picture in your mind. Okay. I'm telling you, and that's an exercise that I must admit I've not worked out completely, but it's true, that the definition is independent of the choice of the singularization. I have not worked it out because I've worked out similar things in the past. I just haven't had time. And this in particular, another part of the exercise, that this makes the delta F a proper birational invariant of F. So what do I mean by that? I mean if I have, so I have never assumed that Y is proper. So if I have a proper birational morphism, and maybe Y1. So this is proper birational. Then I can pull back X and take its main component, of course. And what the delta that occur here and the delta that occur here are related to each other by saying that they are the same. The same valuations occur with the same multiplicities. The point is that the set of divisorial valuation is the same from here to here.
So you can actually compute it. There does exist a y prime where you can actually compute it correctly, isn't there?
Compute what?
The delta F.
Yeah, you can compute it as yeah.
Like as long as the discriminant is normal crossings or something like that.
Well, I'll get to that. That's probably true, but what I really understand is when the map becomes a toroidal map. Then I know that you can compute things from there on.
I see. So it's not quite a general B divisor. Because you don't have to
It's not a general B divisor.
carry out the
So now I define the B divisor associated to a morphism, and I define, and now you might really hate this, a general Campana constellation to be a variety with a B divisor which looks like that in the sense that locally in the Hotal topology of Y, there is a map X to Y that gives you this divisor. Okay? So this is my definition. This might feel really funny because in order to describe such a thing, I need the map X to Y. So it seems to be dependent on maps, but in fact, later on I'll show you that this is truly a combinatorial thing. You can say combinatorially whether a B divisor occurs there. And for that, at least in characteristic 0. And for that, I need to use some non-trivial theorems. I'll define morphisms in a minute. I will define morphisms in a minute. This is part. I mean, this is an important question. I see that my time is basically over. And so let me just say So you just asked, so why don't I answer? I don't know who asked this, but the answer is here. So suppose I have two Campana constellations. I mean, I would be really unsatisfied if I couldn't define maps between Campana constellations. And so what I do is I define the Campana constellation base. So I have a Campana constellation upstairs. I want to define a Campana constellation base downstairs. And in terms of that, I'll define when a map of Campana constellation, a map of varieties is a map of Campana constellation. So the Campana constellation base associated to a map and a delta x is defined as follows. For each divisorial valuation on y and each divisorial valuation on x with center D dominated the center of V, you define the multiplicity of the center above to be the multiplicity that is, what? No, the multiplicity of the center downstairs to be the multiplicity upstairs times the multiplicity that the valuation occurs. And then I define the multiplicity of the thing downstairs to be the minimum of all these relative multiplicities. And the delta V to be 1 minus 1 over mv. So this restricts to the definition I had before in the case where the constellation structure on X is trivial. So I forgot to say, when is the constellation structure trivial is when it's given by the 0B divisor. Say again? Oh, you mean here? Okay, so remember, a divisorial valuation is the valuation associated to x to y is a map of Campana constellations if the multiplicities have this inequality. If the multiplicity, if for every valuation downstairs and any valuation above it, the multiplicity downstairs is not more than this relative multiplicity that I computed here. In other words, I want the multiplicity on y to be less than equal to the Campana constellation-based multiplicities. The divisor to be less than. So it's always the case that Campana constellation maps to the trivial Campana constellation of the same variety. And this just generalizes it. And I think this is a good place to stop because now I define for you a category.